First realize
Okay.
that we didn't talk about that. All right. So I believe last class we stopped on the whole aspect of using the right hand grip rule and using the corkscrew, the right hand corkscrew method, right, to highlight to us the different, how the magnetic field is going to revolve around a solenoid, right? I would say that solenoid is pretty much a coil of wire, right, wrapped in a circular motion, right? So we did talk somewhat about that. Now, typically, when you have a solenoid, it basically acts like a magnet, right? Based on this diagram here, this section is going to be the south part, the south pole, whereas this end is going to be the northern end, right? All right. One of the reasons why we said that was that when we mapped out the magnetic field, we realized that, remember, that your magnetic field, right? It Whenever you're talking about the north pole, the magnetic field, the arrows normally come from out of the north, right? So right here, we see the cursor is the magnetic fields push from that end. So when you did the mapping out and you realize that, hey, my magnetic field is coming through this side, then it shows me now that this side of my solenoid is going to be the north pole. Whereas now, whenever I see that my arrows are going inside this way on the other end, then it's going to show me that this is a south pole, because a typical bar magnet, right? The magnetic field moves out of the north and goes into the south. So that's how we were able to use this whole thing to determine that, right? Okay. No, I think we would have stopped somewhere around here to talk about electromagnets, right? So if we were in the lab right now, we could have set up a situation like this where we get a soft iron rod or a piece of nail, right? And wind some conducting wires, right, around this soft metal. Now, if we have a circuit, it means that charge or current is going to flow through the wires. Remember, we said that whenever you have current flowing through a wire, there is an associated magnetic field that is there. So that magnetic field around the coil is going to cause this soft iron to be magnetized, and by it being magnetized, now we can now use it to attract smaller iron nails, right? So that's how it would work, right? As you using an electromagnet, or you using the concept of a magnetic field being induced by a current carrying wire. So let me also say this, right? Even if the wire is insulated, right, there would still be that magnetic field. But it depends on how thick the insulation is, though, the insulation. But for the most part, if you're using, relatively, thin insulation wires, then, the magnetic field should be felt around the soft iron rod, right? So this would have been the procedure that we would follow, right? And they also said that if we want to make the soft iron rod a much of a stronger magnet, one of the things you would do, you increase the number of turns. When we talk about of turns, talking about the number of circles or number of coils. I will make that sound. Alright, welcome, mute it. Mute it up, I am it being nice. Yeah, walk through some bush. Alright. So in order for us to increase the magnetic field, or the strength of your soft iron rod, you now have to consider increasing the number of turns. So whereas you have 1, 2, 3, 4, 5, 6, 7 turns, you're going to wrap more of the turns around that piece of wire or piece of metal, right? So that in itself is going to give rise to a stronger magnetic effect in the same direction of, and the magnetic effect add to a stronger field. You understand? So by you increasing the magnetic field, it's going to have a much stronger effect. You understand? What else are they saying now? So they're talking about the magnetic domain. Remember, we're talking about the magnetic domain in probably the first class or support, where, you know, in order for this thing to work, right, you have to use a soft iron. If you don't place a soft iron inside of it, it will be hard for the domains to be realigned quickly so that it can become a magnetic material. You understand? So the material that you use has to be soft iron, and because when it is soft, it means then that the electrons, which is basically the domains, would be much easier to realign themselves inside of the metal, so that it can now become easily magnetized. Also, it says that by using a very large current in the coil, this can basically increase the magnetic effect. So remember now, by you increasing that flow of charge, right? You know, charge is moving much faster, which means then that the magnetic effect that is produced by the charges or the electrons moving in that wire has to increase, right? So that's some ways in which we can take advantage of the concept of electromagnetism. All right. Now, here is the point that I wanted to go to, where it says that soft iron is a form of iron that is easily magnetized and demagnetized. You know, the word demagnetized would mean that the opposite, so to speak, right? Magnetically soft and hard materials will be discussed in the next few pages. Now we need to talk about some uses. So just now we realize that we were able to use an electromagnet to attract things, you understand? But now let's take it up a notch now to the world of, you know, electronics and how, you know, certain things work, so to speak, right? Now, electromagnet, right? It's they're saying that it's one of the most common use of electromagnetism, and you know, it's when you're creating what we call a relay circuit, right? So electromagnetic relay circuit, it's going to involve you using magnetic forces to, you know, either turn off or turn on something, so to speak, right? Now, I don't remember if I did this thing with you guys. We're talking about a bimetallic strip. I think we did, maybe not. We're talking about circuit breakers, right? But yeah, if you don't remember, that's fine. But typically, here I have a circuit, and then now within this circuit I have what we call a solenoid. So there's a soft piece of iron inside of here, and the current wire is being wrapped around it. So we expect that once there is current flowing through this wire, there's going to be a magnetic field. Now when you have a magnetic field being applied here, you're basically creating a magnet. The soft iron is going to become a magnet, and magnets attract to other objects, other magnetic objects. So we expect now that the iron armature, right, is going to attract to this end. So we see this red arrow here, it's going to pull this thing towards it. Well, you know, if you're talking more like of a seesaw situation, when you apply more force on this end, right, I expect a reaction on the opposite end. So using the whole aspect of moments, right, clockwise moment equals to anti-clockwise moment. So once I move in the anti-clockwise moments, clockwise moments here, because of that force of attraction, now using my pivot is going to turn this end in this way, in this clockwise position. So now I expect that, you know, the contact or the pivot or this piece of metal, this small iron here, is going to push up, and by pushing up, it's going to touch the contact. So two metals now are being touching each other, and by touching each other, you're going to create that flow of charge, you know, and basically it acts as a circuit, as a switch, I must say. So it's going to turn off and turn on, right? So whenever the metal become magnetized here in the iron core or this iron, whenever it become magnetized, I'm going to expect that current is going to flow through the circuit here because the contacts are going to touch each other, right? Then now in the event that there's no current flowing, then I expect that this thing is going to lose its magnetization because it's a soft iron. It loses its magnetization. This thing here is going to go back to its original position, right? And then now, as a result of that, the contacts will no longer be there. You understand? So no current is going to be able to flow through this, we call it stringy metal. All right? So that's one way. That's just talking about how the switch works, right? Or how the relay switch works. So by the way, guys, here is a symbol that would represent an electromagnetic relay. So in the event you may see a multiple choice, this is what it is, right? Good. So now let's look at how we actually use this in a sense. So when you're starting your car, basically, right? This is how it works. So once you turn the ignition, right? You're basically allowing current to flow through. So your battery is in the car, obviously, and once you turn the ignition, you're now prompting current to flow through your circuit and causing this thing here to become magnetized, right? Remember, if a person who ever started a car before, when you turn the key over, you understand, and you start the vehicle, you release the key and the key come back to our original position, to another position. So if you look at it, when you turn the key over, it does not stay in that fixed position. It comes over. So what it does really is that you're basically pushing the contacts, or you're basically allowing the metal to become magnetized. After it becomes magnetized, it's going to start the motor. Once you start the motor, it's going to know you just need to, you don't need to have it be in contact again because already started the motor and the car is now traveling on its own. So that's how it kind of works. Once you turn the key, it's going to trigger the circuit. It's going to trigger this thing to become magnetized because as you can see, this wire is connected to this thing here. This what do you call it? This metal, all right, and it's going to become magnetized. So by becoming magnetized, now it's going to push down on the contact, right? So this relay is going to touch down here and cause the motor to start. So that's how the car basically starts, right? Are there any questions? Hello?
Oh, sure.
You understand what I'm going by the way?
Sure.
Sure.
Who ever started one car before?
Me, sure.
And you realize when you turn over the key, right? The key come back.
Yes, sir.
Good. Now, if you go drive your parents' car or try run out them car for road now. You know some other you want to experiment on a science student. But yeah. So that is what is happening. The circuit will work. So that thing becomes magnetized. Then now, here what now? We have a little spring here. So how the spring works, the spring is going to extend. And how spring normally works, guys, is that, so that force now is pulling down, right? Because of that magnetization, the spring is going to extend. Now, whenever you release that circuit, whenever you break that circuit, the spring is going to retract and come back. So, So that's what it is in a nutshell there. Now, when you hear the bell ring at school, so we have looked at two ways. Well, basically, there are three ways how this thing works. We looked at the circuit there with the starting the car, and now we're looking at how the bell works. You understand? So when you're at school and you hear the bell ring, this is what is happening. Once you press the bell button, once you push the button, you now create a magnetic field around this coil. Now this coil is going to become magnetized. Let me see what's happening. So the coil becomes magnetized, and by becoming magnetized, this soft iron core is now going to become magnetized as well. And what you're going to find is that it's going to cause this hammer to beat along the bell. So yeah, so that is what is happening. You understand? So whenever you hear the bell ring, it's because of an electromagnetic circuit that is allowing to work. And This is something we can do in the lab, maybe in the future. Me teaching physics, I'll do something like this. I've never done it before. I would like to do it. This is to show students how the whole electromagnetic induction and stuff like that work. Or So we said that electromagnet can also be used in electric bells. When the switch in the bell circuit is closed, the electromagnet attracts the soft iron armature, and the hammer strikes the bell. The contact is broken at P, causing the coil to lose its electromagnetism. The spring then pulls the armature back to the original position and make contact at P. So typically what I just said, they're just reiterating that. All right, now we're talking about domains. I actually drew a diagram showing something like this. Cool. So this is what is happening inside any material that is able to become magnetized, right? So we have different domains here. So it suggests that magnetism is caused by moving charge. And we hope we're listening. Somebody's kind of making a sound here. All right. Yeah. So it is suggested that magnetism is caused by a moving charge, and it's clear, right? As electrons orbit an atomic nucleus, a loop of electric current is produced. So inside of an atom, right? Whenever it is orbiting the nucleus, there is a small amount of current that is produced there, because of that movement of the electrons around the positively charged nucleus. Good. This results in the formation of a tiny magnetic dipole. Cool. So once you have that movement taking place there, there's going to be now a magnetic field going along here. And so whenever now you apply, current to a conductor, those electrons inside of the conductor are now revolving around their nucleus and moving much faster, creating more magnetization, right? So that's what is happening there. Now there's a thing though that they're saying that if as many electrons orbits one way as orbits the opposite way, the magnetic dipole effect are opposite and cancel each other out. So what they're basically saying is that if I have X amount of electrons going in this direction, right, and then now I have another set of electrons going in the opposite direction, right, they're going to produce, one is going to produce a magnetic field that is going to basically cancel out the other one. You know what I mean? And with that now, that is how materials that are not able to become magnetized, that's how they actually work, so to speak. Right? And it says this explains why most substance appears non-magnetic. All right? Now we highlighted some of these substances already. We talked about iron, nickel, cobalt, right? Those are groups of metals that are things that basically have domains that are able to become magnetic, so to speak. See? So within each domain, the magnetism due to each of the atoms adds up to produce a large magnetic effect. So after you apply the magnetic field, or after you apply the current rather, what we expect, it will be looking similar to this. You understand? So in its natural state, this is what is happening here. But whenever you apply now, the current to it, or another magnetic field, these domains are going to line up facing where that magnetic force is applied to it. And as a result of that, if the material is a soft material, it will retain it for a period of time, then it will lose its magnetization, then it will go back into this position, right? Now, when you have substances that are able to realign their domains to become magnetic materials, then we refer to those as ferromagnetic materials, right? So ferromagnetic materials are those that are able to the domains are able to realign in a direction in which the magnet is applied to it. You understand? And then now these are the materials that would form what we call soft magnets, or permanent magnets, or temporary magnets. All right. Some important point here. It says magnetic domain within an object made of a ferromagnetic material can be enlarged by cooling the object. So what they're saying here is that if the object is more cooled, right, we can basically enlarge the magnetism, or the magnetic domain. So let's see what it's saying as well. It says, as the object cools, less energy is available for atoms to vibrate randomly. So typically inside of the atom, right, or if you apply heat to a metal, you're going to find that there's going to be more vibration. There's going to be more electrons colliding against each other. So with that, now when you cool the thing, right, you have less of that vibration, so to speak. So you are more able to retain the permanency of the magnetic material, so to speak, right? Because you don't have the electrons trying to push themselves all over the place, changing the domains and all those kind of things. So yes, so as the object is as you cool the object, we expect that less vibration is going to take place. Thus, it says more atomic dipole lines up in the same direction. So because you're lining up with each other, right, you're becoming a much stronger domain. You understand? They say the stronger, whenever you have a chain, right, the chain is connected to a link, and the longer the chain is, the more stronger it's going to become. And this is similar to what we're doing here. So the magnet becomes more powerful, right? Now they also said that heating the object causes the particles to vibrate. The domain then becomes smaller because the atomic dipole takes up different direction on account of the increased vibration. So what we see happening now is that anytime you apply heat to a magnet, you're basically interfering with the domains. You understand? Right? And with that, it can cause the object to lose its magnetization. See? So it says magnetic domains in a ferromagnetic substance can also be enlarged by placing the substance in a magnetic field. Sure, so if it's a magnetic material and you want it to become magnetized, this is one way how we can make a magnet becomes a much stronger magnet, by taking it and placing it inside of a magnetic field with a stronger magnet. All right. Under the influence of the field, many magnetic dipoles line up in one direction, and they merge to produce a larger one. It's just concrete on what we talk about with hard and soft magnetic material. We have said it before, we're going to say it again. So a material is said to be magnetically hard if it is difficult to change its domain structure. Such substances are hard to be magnetized, and they are also difficult to demagnetize. So a hard metal is going to be one that it's going to take long for the domains to line up. However, when the domains do line up, it's going to take a longer time for it to become demagnetized, right? Because they tend to retain whatsoever magnetism they have, right? And those are what we call permanent magnets. We're now.
Sir, so after a while, the hard magnets then lose the magnetism?
Can lose some amount of the magnetism, and it depends on the condition. You understand? Right? If the conditions are perfect in the sense that you don't have any heat or any vibration taking place inside of the material, then it will retain it. You understand?
Yes, sir.
Yeah. Now we made mention of the different types of permanent magnets or materials that would classify as permanent magnets, right? So steel, right? And steel in this case is made up of carbon and iron, right? I don't know what is this, alnico, right? That is made from aluminum, nickel, and cobalt. So I'm guessing they just put all the words together. Al comes from aluminum, Ni is nickel, and Co, which is come from cobalt, right? Manduru, right, is another one that we talked about, which is basically an oxide of metal and barium. Yeah, right. So that's how manduru is formed, right? And we say that permanent magnets are therefore made from magnetically hard material. So if we understand what is a magnetically hard material, then on the other end we must understand what happens to a soft material, right? So if you look on this side, this is what is happening, would happen inside of any kind of material, so to speak. Once it becomes magnetized, right, this is what is going to happen. The domains are going to line up behind each other, now forming what we call stronger magnetic effects, right? So we don't even bother explain the whole soft magnet material, because that, by the way, I have about 5 minutes on this session, so once it closes up, let's click on the next one. We click the same link. So with a soft material, right, those are what we would call now the temporary magnets. So when you look at the school bell being ringing, right, if it wasn't for the fact that they use a soft material, that bell would have been just ringing and making noise on your head. You understand? But no, because they use a soft material, it is now able to become magnetized easily and loses its magnetism much quickly, or in other words, becomes demagnetized much easier. So that's what we call temporary magnets, right?
Sir.
Yeah.
Sir.
Go ahead, ma'am.
You're going to send this video in the group, right?
Why? Why you ask?
Because me, if you look back on.
Oh, you need to look back on it. I will ask me that question then.
Campbell.
Oh, okay. All right, yeah, man. I normally try to post the videos. If you tune in into my YouTube page, you'll see when I post them. I ain't gonna tell you when I post them. Just keep tuning in and watch those videos. You understand? Click that bell button and subscribe for more videos. You understand? Don't know what things say.
Okay, sir. What's your name on YouTube?
So it is Ray's Tutoring JA. So it is RAE apostrophe S. Ray's Tutoring JA.
Okay.
So you haven't looked at it as yet then.
Okay, sir.
Yeah, man. All right. Either way, we're going to talk some more about this. This is something that we need. We must talk about. Right? We must talk about how you can make a magnet. Right? So method of making magnet. One method is by striking, or stroking rather. Right? And that is when now you take a magnet, in this case, and you just motion it. You just like when you are striking a match, right? You would just go ahead continuously moving that thing alongside the object that you want to become a magnetic material, and over time the domains will line up and making that material a magnetic material. There is also the electrical method. An electrical method is simply.
How long would that take?
Huh?
How long would it take?
Depending on the type of material, I can't say, I'm not sure, but it shouldn't take long. It definitely shouldn't take long. I don't know if persons have used like a screwdriver before, and you running that screwdriver on a screw, you realize that it becomes magnetized very quickly. You have some, yeah. And then after a while, you realize that that screw can attract other stuff, or that nail can attract other things. So that is basically what it does have to be long. And sometimes you don't even have to even strike it, you know. Once once the magnet that you're using is very strong, then it shouldn't take long.
Yes, sir.
Typical method now would be similar to what we talked about when you're talking about a solenoid, and you have the rod, you have the iron core inside of the solenoid. Once you apply a voltage or a current to that coil is going to induce that magnetic field and make that thing becomes a magnet. And we know for sure that it has to come from the fact that the domains are in line with what is happening here. So demagnetizing a magnet now, right? I don't know why you want to do that, but yes, there is a method in which we can demagnetize a magnet. So demagnetizing a magnet involves randomly disturbing the alignment of the domains. And that's what it basically would be, right? So this can be done by repeated mechanical shock. For example, by dropping the magnet onto a hard surface. So that's one way. Another way is like heating the magnet and allowing it to cool in the east-west direction. So we'll talk about that when however about less than a minute, I think. Right. So once you cut off, we'll just pick up that point.